Okay, so we're going to look at the standard enthalpy of hydration. Enthalpy of hydration is the enthalpy change or the energy change. What have I got here? Oh, I do have sodium chloride. Why would it not be sodium chloride? The enthalpy change of sodium chloride when 1 mole of gaseous ions is, so the phrase usually used is infinitely diluted, which sounds like you have to put 1 ion of sodium in the Pacific Ocean, but actually ions become infinitely diluted, which infinite dilution means the ions are no longer interacting with each other. You don't need an awful lot of water to infinitely dilute. But I'm just going to say 1 mole of gaseous ions are dissolved in aqueous solution. So in other words, if I start off with a gaseous sodium atom, sodium ion, and I make it into an aqueous sodium ion, then that difference there will be the enthalpy of hydration of sodium. The equation, sometimes you'll see we're adding aqueous on the left, as if aqueous is a thing. I mean, obviously you're adding water, but sometimes it's just shown as AQ added on the left. Okay, so that's the enthalpy change. Now we can tie that into lattice formation enthalpy, because you will remember that if I start with solid sodium chloride and I turn that into gaseous ions of sodium and chloride, gaseous ions, then that is the enthalpy of lattice dissociation. Dissociation, because I'm turning the compound, the solid compound, under standard states and conditions, into gaseous ions. Big positive number, usually. I can't remember what it was. Plus 786. Okay. And now we can use our new exciting enthalpy of hydration to turn our gaseous ions into aqueous ions. So that will be the hydration enthalpy of sodium, and that will be the hydration enthalpy of chloride. And now, as you can see, it's getting a sort of familiar Hess cycle look, isn't it? Plus AQ. Here, I have the enthalpy of solution, not to be confused with hydration. Enthalpy of solution is the enthalpy change when 1 mole of salt in its standard state is infinitely diluted, dissolved in aqueous solution. So, enthalpy of solution of sodium chloride across the top, enthalpy of lattice dissociation here, or I suppose you could have formation there going in the other direction, and then our new enthalpy of hydration there. Now, let's just do the numbers first, shall we? So, enthalpy of hydration of sodium minus 406, enthalpy of hydration of chloride minus 364, and so going from left to right, the enthalpy change when I dissolve a mole of sodium chloride in water would be plus 786. And then we're going in the same direction for all the arrows, so all the signs will stay the same. Minus 406, minus 364. You can see how it almost cancels out. Plus 16. So it's a very small number. It's also a positive number, slightly endothermic. So if I dissolve sodium chloride in water, I'd expect it to get cold. But it's interesting to note how these two processes kind of oppose each other, breaking the sodium chloride up into ions. And remember, some substances have much higher lattice dissociation enthalpies, especially if you've got small highly charged ions like magnesium or aluminium. It's interesting to note that all sodium compounds are soluble. Lots of magnesium compounds are insoluble, as are lots of aluminium compounds, because we're taking more energy to break up the lattice here. Now, we get some of that energy back when the ions form bonds. They form bonds with the water molecules. So if I have a sodium ion, when that gets into the water, remember a water molecule is polarized with a slightly negative oxygen and slightly positive hydrogens. So the slightly negative oxygen, if I draw my little water molecule like a sort of Mickey Mouse like that, the slightly negative oxygen is going to stick to the sodium molecule. I'm not sure about the sodium molecule. Let's just start that sentence again, shall we? The slightly polarized water molecules stick to the sodium ion. There we go, like that. The scale's all wrong, but you get the idea. Of course, if I was looking at chloride, it'd be the other way around, right? It would be the positive ends of the hydrogens would stick to the negative chloride ion. Okay, so as the ions are surrounded by water molecules, the formation of that's not quite a bond, is it? But that attraction between the positive ion and the delta minus negative oxygen, that releases a bit of energy. So hydration enthalpy is always going to be delta H negative, it's always going to be exothermic, and lattice dissociation is always going to be endothermic. We always have to put energy in to break a lattice because we're breaking bonds, which means that enthalpy of solution is going to be kind of the difference between the two, and that accounts for why some things are soluble and some things are insoluble. If this is a big positive number, if we have to put a lot of energy into dissolving a substance, then it won't dissolve, not at room temperature anyway. Another thing we could note here is why does the reaction happen at all? If it's endothermic is kind of uphill as far as the universe is concerned. We have to put energy in. Why does it happen? It's interesting to note sodium chloride is not super soluble. You can only dissolve about a teaspoon of sodium chloride in water, in like a glass of water. So it's not super soluble, but why does it happen at all? We'll come back to that question in the next part of the topic. Okay, let's just do another one of these. Let me find another example. Okay, I can't find another example. Bear with me. No, I really can't. Oh, there it is. Yep. Calculate the enthalpy of solution for magnesium chloride. We've got some data there. So let's get our Hess diagram done. So we start off with the solid compound on the left, and we dissolve that by adding it to aqueous to make aqueous ions. Okay, that's our enthalpy of solution right there. That's the thing we're trying to work out. We've been given the lattice formation enthalpy. So the lattice formation enthalpy is the enthalpy change when 1 mole of solid magnesium chloride is made from the gaseous ions. So that's the lattice formation enthalpy for magnesium chloride. That'll be a big negative number. And then we've got separately the hydration enthalpy for magnesium and the hydration enthalpy for chloride. But of course, we've got 2 chlorides in magnesium chloride, so we will need to multiply that by 2. Okay, as always, the mistakes in these kind of topics come from forgetting to multiply something by 2 or multiplying it by 2 when you don't need to. Minus 2502 for the lattice formation enthalpy, big negative number. Magnesium here is minus 1920, and then minus 364 for each hydration enthalpy for chloride. So going across the top, enthalpy of solution for magnesium chloride will be, well, I'm going in the opposite direction to that arrow, so I need to change the sign there. And then I've got minus 1920 minus 2, oh, sorry, plus 2 times minus 364. It doesn't matter where the minus sign goes, but it needs to be in there somewhere. And I don't know what that is. 2 times minus 364 minus 1920 plus 2502 gives us minus 146 kilojoules per mole. Magnesium chloride is a very, very soluble substance. We can dissolve lots of it because, as far as the universe is concerned, that is super downhill.